Hello everyone, this is Raghunath from SuMON Math program. In this video, we will solve a problem from SuMON Math. This is a level 3 problem of fortnight 9 and this is an interesting one related to combinatorics and recurrence relations. Let's look into the solution and the problem. So here is the question that states that on an n cross n board, the set of all squares that are located on or below the main diagonal of the board is called the n ladder. For example, if you consider the 3 ladder, you need to start with a 3 cross 3 square which has 3 columns and 3 rows like this, and consider all the unit squares on diagonal or below it. This is the diagonal, the main diagonal, and here is the 3 ladder structure. Okay, so what should we do on this 3 ladder? In how many ways can a 99 ladder be divided into some rectangles which have their sides on this grid lines in such a way that all the rectangles have distinct areas? Let me give you an example for 3 ladder. Here is the structure as we saw, and one division could be into this rectangle and this one, which partitions into rectangles of different areas, and all the unit squares of this 3 ladder is covered in it. As the areas are 1, 2 and 3, it is clearly distinct. So this is one possible way to divide the 3 ladder. Like this, how many total ways are there to divide this 3 ladder? But let's derive a expression for general n ladder. It will not be difficult, as you will see. We will use an idea called as recurrence relation to deal with this problem. At first, let's do some definitions and then let's derive this recurrence relation. Here is the first definition. In any n ladder, call the unit squares on the diagonal to be a diagonal square. For example, in 3 ladder, these are the diagonal squares. There are 3 diagonal squares. Similarly, in n ladder, there will be n diagonal squares. And notice that in any rectangle, there is at most 1 diagonal square. There can't be 2. The reason is being that they are structured in a diagonal way. They cannot, and with the top right square missing, they cannot be accommodated in a rectangle. So here is our first observation. Each rectangle contain at most 1 diagonal square. Now this means that there are at least n rectangles in our entire subdivision because there are n diagonal squares. So number of rectangles in the division must be greater than or equal to n, because remember, the entire ladder should be subdivided into rectangles, and since each rectangle is containing at most 1 diagonal square, there are at least n rectangles in the subdivision. Right, so now let's come to the total area argument. Assuming that each unit square is of area 1, what is the total area? Think about it. What's the total area? In row 1, there is 1 unit square. Row 2, there are 2 unit squares. In row 3, there are 3 unit squares, and so on. So total area is nothing but 1 plus 2 plus 3 till n, because that is the number of unit squares in each row, which in turn represents the area. And this equals n into n plus 1 by 2. But if you are arguing with the number of rectangles in the subdivision, let's see what can be derived. Clearly, there are n rectangles and each rectangle is having distinct area according to the question. So total area must be greater than or equal to 1 plus 2 all the way up to n. This is because of the fact that there are at least n rectangles as we derived in the previous step, and that the areas are distinct. There is no repetition in area, which is n into n plus 1 by 2. But we know total area is n into n plus 1 by 2. So the equality condition is being true. And when will it be true? It will be true when there are exactly n rectangles in the subdivision, each with area 1, 2, so on till n. So since the equality holds, after the subdivision into rectangles, we have exactly n rectangles with areas 1, 2 and so on till n. These are the areas, because the areas can't be more than that, as otherwise the sum would be more than the total area n into n plus 1 by 2, which is a contradiction. This completes our second observation. Going on, notice that the bottom left unit square must be contained in some rectangle after the subdivision. Let's think about which rectangle could it be, and you will be surprised of the result. So let's say this is the n ladder that we are talking about, and also notice this, that each of these rectangles should also contain a diagonal square. This is because there are exactly n diagonal squares and there are exactly n rectangles in the subdivision. So, and also each rectangle should contain at most one diagonal square. This means, as a third observation, we can also tell that each rectangle contain exactly one diagonal square. And suppose you consider the rectangle containing the bottom left square, and here is the bottom left square, which suppose contain this corner square, this corner diagonal square. So it would look like this. That is the rectangle containing that corner diagonal square, and thereby completing the rectangle. Now, after removing this rectangle, you will have two ladders. Let's say the sizes are M1 and M2. In these ladders, we again subdivide them into rectangles, and we know that the subdivision must contain areas numbered from 1 to M1 and here 1 to M2. But this means two areas are being equal. For example, 1 and 1 is equal, and we can't allow that, right? This means that this rectangle containing the bottom left square cannot have this as its diagonal square, which is in the middle of the diagonal squares. That means consider the corner diagonal squares. Let's say this one. Then this would not contradict, or this corner diagonal square would form this rectangle, and this also would not contradict the formation of two different ladders after removing this rectangle. So hence, the rectangle containing, this is the fourth observation, rectangle containing the bottom left square must be of size 1 cross n or n cross 1. N cross 1 is the vertical rectangle and 1 cross n is the horizontal rectangle. Alright, so we have couple of observations here, and let's use them to arrive at the conclusion. Let's say an denote the number of ways to subdivide a n ladder into rectangles, which was asked in the question, we know that. So what is its relation with the n-1 ladder? That is the idea behind recursion. We know that there must be a 1 cross n or n cross 1 rectangle divided from this ladder. So let's say this is the ladder and we have removed this rectangle from the ladder. Then this corresponds to a n-1 ways to divide this n-1 ladder, because removing the bottom row would form a n-1 ladder and an-1 is the corresponding number of divisions. And similarly, we can also consider the n cross 1 rectangle, which is vertical, that is containing the bottom left square, and let's say it is removed, and that remains with n-1, again giving us an-1 ways to divide. And these are independent because the bottom left square is contained in a vertical rectangle, but in the previous case it was contained in a horizontal rectangle. Now these two gives us the overall count of a n ladder, because there are no other rectangles in which the bottom left square can be. So we have considered all the ways. So this implies an equals 2an-1. Tada! We have arrived at the recurrence. Now we know that initial condition is required to solve the recurrence. What is the initial condition? The initial condition is for the one ladder which is just a unit square, implying us that a1 is 1, because this is that rectangle, there is no other way. And you will easily see that a2 is 2 times a1 by the recurrence, which is 2, and a3 is 2 times a2, which is 2 squared, and a4 is 2 times a3, which is 2q, and so on. And in general, we can prove that an is 2 power n-1 for all n in natural numbers. So this relies on recurrence, which is the assumption about a ladder of dimension 1 lesser than the actual ladder. I hope you enjoyed this video. The link for this notes will be provided in description. You can download it from there.